Hey everyone, welcome to Neil's Not So Boring World of Chemistry. I have a question for you. Do you know what a buffer is? I mean, how do they work? What do they actually do? And finally, if I need to make a buffer, how am I supposed to do that? Now, if you're studying acid-base chemistry, you probably find yourself asking some of these questions, and I'm here to help you. In this video, I'm going to dismantle any confusion you have about buffers, what they do, and how to make them. And I'm going to really try to guide you toward a complete understanding so that you can answer questions about buffers all on your own.
What's up, everybody? Welcome to Neil's Not So Boring World of Chemistry. Let's go into the lab and take a deep look.
Okay, so we want to know what a buffer is, so we look it up in a dictionary. We find that the definition is a person who prevents two antagonistic people from harming each other. As a verb, it means to lessen the impact of something. But what about in the context of chemistry, or more broadly, scientific discussions? Focus on your body for a second. The blood coursing through your veins has a pH of about 7.4. If you contrast that with your stomach acid, you'll find a pH of about 1.5. Now, these pH values are essential. If these bodily fluids are to do their jobs, that pH has to remain within a very strict range. Luckily for us, they're buffered. In biology or chemistry, a buffer is a solution, which means some stuff dissolved in water, that is going to resist or lessen the impact of adding acid or base. So in other words, if you add a little bit of acid to your blood or a little bit of base to your stomach acid, the pH should not change very much at all. And that's what buffers do.
So before I talk to you about how buffers function, I want to make sure you have some required background knowledge. Do you know your strong acids? Recognizing these 6 chemical compounds by both their name and their formula is really important. Likewise, I suggest familiarizing yourself with the strong bases. Now, why do we want to know these strong acids and bases? Well, they cannot be part of an effective buffer system. So sometimes they come up in a question and we want to recognize them immediately. There's also the issue of conjugate acid-base pairs. By definition, a conjugate acid-base pair can only differ by one single hydrogen atom. That's the only difference. Take a second and look over the examples I've provided. Do you notice that the only difference between the compounds in each example is a single hydrogen? Now, of course, when you add a hydrogen or take one away, it can affect the charge. But in terms of the atoms involved, the only difference can be a hydrogen. All right, now we got that stuff out of the way. Let's think about how buffers are able to maintain pH levels.
Now, the first thing you need in any buffer system is a weak acid and its conjugate base, or a weak base and its conjugate acid. And weak is really important. So sometimes people ask, well, why can't you make a buffer out of a strong acid and a strong base? Wouldn't that make a stronger buffer? And the answer is no. It actually wouldn't make a buffer at all. If you look at this reaction here, we have a strong acid reacting with a strong base. So imagine we add these two things together to try to make a buffer. And what happens is we just produce a salt and water. Now, how is water and a salt going to prevent changes in pH? Well, to be honest, they can't. Oops. So that's why we need a weak acid and its conjugate, or a weak base and its conjugate. Okay, so right here we have a quintessential weak acid conjugate base pair. This is acetic acid, and its conjugate base is the acetate ion. Now let's say I actually wanted to make a buffer out of these two components. They're totally suitable. But when I go into my chemistry closet, I'm going to have an issue. I'm going to find some acetic acid, but I'm going to notice that there's no bottle labeled acetate ion. And that's because ions like acetate usually come in the form of salts. So what I'm much more likely to find is a bottle of sodium acetate. Now this is totally fine. Why is that? Well, this is an ionic compound and it contains an alkali metal, so it's super soluble in water. So when I take my sodium acetate and I dissolve it in some water, the sodium is going to dissociate and disappear. Well, I shouldn't say disappear, it'll be in there, but it's not going to be active, right? So now I'm going to have my weak acid and my conjugate base. Okay, now we're ready to consider how our weak acid conjugate base system, working in tandem, are going to be able to dampen the effects of any additional acid or base that's being added. Let's start off with the base first. Now we know when we add base to something, what we're essentially doing is increasing the concentration of hydroxide ion. So let's say we did that. Let's say we added some hydroxide ion. We would be concerned that the pH would go up, right? But watch what happens in this buffer system. This hydroxide is going to react with our weak acid. Now essentially what it does is the negative charge of this hydroxide will pull off this hydrogen. And what's the result going to be? Well, we're just going to get some of our conjugate base and H2O. So essentially the hydroxide is neutralized. It's consumed by reacting with the H of our weak acid, and we don't have to worry about the pH going up. Now on the other hand, what happens if we add acid? If we take that flask and we pour it into our buffered system, what we're going to see is the addition of H+ ion. Now in this case, we've got our acetate present to totally take care of that. There will be a reaction between the negatively charged acetate and those H+'s from the acid, and the resulting product will be our weak acid. So as you can see, in a buffer system, the addition of moderate amounts of OH- from a base will be counteracted by the weak acid. On the other hand, the addition of H+ from an acid is going to be counteracted by the acetate ion or the conjugate base. So we can add a little bit of acid or a little bit of base, and these two components will be able to take care of those and convert them into things that don't really affect the pH, like water or a weak acid or a weak conjugate base. Okay, so now I want to talk to you about a practical way to make a buffer. Now, the ideal method that people usually use is you'd go into your chemical cabinet, you'd locate the weak acid that you're interested in this case acetic acid, and then you'd look for another flask that contains the salt of its conjugate base. So we discussed using sodium acetate because we know it's going to dissociate, the sodium will leave, and we'll be left with the conjugate base acetate. So we would look for these two things. Hopefully they would be of the same concentration, and we would probably want to mix them in equal amounts. And this would make a very effective buffer. But what happens if you go into the chemical cabinet and you don't have sodium acetate? In other words, all you have is your weak acid. How are you going to make a buffer with just a weak acid? I'm going to show you how. Okay, so now we're going to learn how to deal with a scenario where we have the weak acid we want for our buffer, but we don't have any of the salt of its conjugate base. Now I want you to think back to our discussion of what happens when a base is added to a buffer system. We said that the additional hydroxide ion would react with the weak acid and we would get two products, water and the conjugate base of the weak acid, in this case acetate. So by adding a strong base, let's say sodium hydroxide, which is really common, it's usually on hand, we could actually convert some of our weak acid into the conjugate base that we need for our buffer. Now we'd have to be careful and deliberate about how we do this, because I think you would agree, if I had, let's say, 10 moles of my weak acid, and I add 10 moles of my strong base, they're going to completely react with each other, and I'm only going to be left with the conjugate base at the end. But that's not what I want, right? For my buffer, I want some of this and some of that. So we can be strategic. We could say, all right, if we have 10 moles of this, let's only add 5 moles of our strong base. And that way, only half of the weak acid gets converted into the acetate ion, and we still have half of our weak acid left. Now, of course, if we have some weak acid and we have some of its conjugate base, we have the buffer that we were trying to make in the first place.
Let's wrap this up by talking about some of the big ideas we've covered. By definition, a buffer solution resists changes in pH. A buffer is made up of either a weak acid conjugate base or a weak base and its conjugate acid. In the lab, we need to oftentimes use a salt that contains the conjugate that we're looking for because conjugates don't typically exist as solutions. A buffer system can neutralize small amounts of acid or base that are added. Of course, there comes a point where if you've added enough acid or base, the buffer system can no longer manage it. There are two main ways of making a buffer. The most straightforward way is to add equal parts of your weak acid or base and its conjugate salt, and you want to make sure their concentrations are consistent. Now, if you only have the weak acid or base, you can use a strong acid or base, and what that can do is convert half of your weak acid or base into its conjugate. Time for a practice question. Please read the question, pause the video, and check your answer. Which of the following pairs could be used to make an effective buffer? Okay, the answer is C. Now we eliminate choice A because HCl is a strong acid, so it can't be part of a buffer. We eliminate choice B because if we look at HClO and ClO2-, we notice that they're not actually a conjugate acid-base pair. They don't only differ by a hydrogen, they also differ by an oxygen. Now letter D is not eligible because barium hydroxide is a strong base. So we're left with C. Here we have HF, hydrofluoric acid, which is weak, and when the lithium fluoride dissociates, we'll be left with F-, the fluoride ion, and that is the conjugate of our weak acid. Okay, here's another practice question. Which statement accurately describes how a buffer system composed of a weak acid and its conjugate base is able to neutralize added acid? Pause the video and check your answer. Here the answer is D. When we add extra acid, what we're really adding is H+ ions, and the conjugate base with its negative charge is going to be attracted to that H+, and in the process it'll consume it and turn it into more of the weak acid, which is unable to change the pH. Thanks again for watching, everybody. Appreciate your support. Please leave comments and questions below, and you can follow me on Instagram at Neil's Not So Boring World of Chem.